Okay, welcome everyone. Today, Kwan Young is going to introduce the wavelet-guided acceleration of text inversion in diffusion-based image editing. Let's get started.
Today, very few people came here, so I prefer but I try to finish my presentation quickly, within 20 minutes, I think. So, hello, my name is Anyaku, and today I will be talking about my research titled Wavelet-guided acceleration of text inversion in diffusion-based image editing, which is submitted to ICASSP conference. And I specifically I'll be focusing on image editing method based on diffusion model. So the contents are as follows, and I'll start with the introduction about current image editing model. 2023 was definitely a year of text-guided diffusion model, which the release of many papers on image generation and image editing. And text-guided image editing task is that if the input image and user's prompt are given, then the diffusion model edit this image to align with this user's text prompt while preserving the original image. And a key point is that how do we preserve this original image as much as possible? And previously, image editing method based on diffusion model struggled to preserve these characteristics of original image. However, with the introduction of prompt-to-prompt and plug-and-play approach, which were submitted to CBPR 2023, it is possible to edit this image to align with user's text prompt. And regarding this approach, the reconstruction is performed first, and during this reconstruction process, the attention features in UNet are saved. And after the reconstruction, the editing process is performed, and the attention features which were saved before are injected into this process. So models like prompt-to-prompt and plug-and-play, which are based on diffusion model, utilize these two diffusion branch methods. This approach consists of source branch and target branch. And first of all, the input image, like corgi image, is converted into the DDI latent using DDI inversion. Actually, DDI inversion is similar to DDPM process, but it removes the stochastic term under a certain assumption like non-Markovian process. So using this DDI inversion, we can get this DDI latent. But I'll skip the detail of DDI inversion. And after we get this DDI latent, then DDI latent and user's prompt goes through into UNet to reconstruct the original image. And during this process, the attention features in self-attention module are saved. And after this reconstruction process, the editing process is performed. And in this process, the attention feature which were saved before are injected into this process. So to this attention feature injection scheme, we can preserve the structure and composition of original image like this. So this is the output of editing results. So, and however, there was a problem. The reconstruction is challenging. So this is because for DDI inversion, Gaussian noise is added to original image, so we can get this DDI latent. But in this DDI inversion process, the conditions such as text or user's text prompt are not taken into account. But in this reconstruction process, we have to consider the classifier-free guidance. And in general, this classifier-free guidance ensured we call it CFG, and in generally this value is set to 7.5, so this CFG accumulates errors, so resulting in an image that differs from the original. So as you can see here, the result of reconstruction is quite different from the original image. So therefore, if reconstruction fails like this, then the editing is also likely to fail. Then how can we improve the reconstruction? To enhance this reconstruction, a method called null text inversion, in short NTI, was proposed in CVPR 2023. And before I explain this null text inversion, let's say the DDI inversion trajectory is ZT star and DDIM sampling trajectory is ZT. Then and DDIM inversion trajectory is so this path refers to the DDIM inversion trajectory, and this path corresponds to DDIM sampling trajectory. And we can see that the distance between these two trajectories and the mismatch between these two trajectories causes the reconstruction to fail. So null text inversion proposed the method that during every denoising step, null text is optimized to insert that ZT star and ZT align closely. So through this method, DDIM sampling trajectory can become identical to the DDIM inversion trajectory. So this enabled the reconstruction successfully. So, firstly, however, there is a drawback of NTI, which is its time-consuming nature. Null text inversion optimizes null text at every time step during DDIM sampling. So the time taken for editing for the image is about 180 seconds, so which is quite long. So based on this problem, we are motivated to reduce this editing process time. So we find that applying null text inversion only up to a certain time step is, rather than the entire time step, is enough for successful reconstruction. Therefore, we proposed the wavelet-based optimization estimator, in short called Wavelet estimator, to predict the endpoint, which is the final time step for optimizing the null text embedding for each image. So we can reduce the editing process time over 80%, like here. So using Wavelet estimator, the editing process is about 30 seconds compared to 30 seconds. And let's move on preliminary analysis. Firstly, we performed the null text optimization analysis, and let's define this pi value as the optimized null text embedding vector. and in here, this t means the time step during DDI inversion and sampling process, and in general, the maximum of this t value is set to 50. It is a commonly used value in DDI inversion. And after that, we conduct a null text optimization from the first of DDI sampling at 50 time step at 50 to a specific time step t star, and subsequently from t star to 1, we just copy the pi value until time step 1. So in short, it is very simple idea. We conduct null text optimization only up to certain time step rather than the entire time step, and we just copy the rest of this pi value until time step 1. And we define the following notation. The first one is t star. T star is the endpoint time step at where null text optimization is applied. And if this value is set to 1, then it is equivalent to null text inversion method. And X origin refers to original image, and X-recon means reconstruction images obtained by adjusting T-star. And we also measure the PSNR metric between original image and reconstruction image. And we define this PSNR ratio comparing the two PSNR terms. And as you can see here, the denominator of this value is PSNR between original image and reconstruction image at time step 15. So this result is about the NTI, the result of NTI. And if the PSNR ratio is high, then it means the input images are very similar. And if the PSNR ratio is lower, then it means the input images are quite different. And as shown in figure 2, let's look at the example with this bicycle image. And at the time step 25, we can see that the PSNR ratio is around 25. And at the maximum time step 15, the PSNR value is around 26. So you can see that the PSNR ratio already exceeds 90% at the time step 25. So therefore, it means it's possible to achieve sufficient reconstruction by optimizing your text only up to specific time step, rather than the entire time step. So to understand how the optimal endpoint T-star varies depending on the image, so we conducted a frequency analysis. Before this analysis, we selected two types of image. The first one is high frequency image, and the second one is low frequency image. And after that, using discrete wavelet transform, we obtained those 4 subbands from the original image X and calculate the energy by squaring the value of each pixel. And in here, the XLR means the expression of low frequency component along x-axis and y-axis, and XLH means the expression of low frequency component along x-axis and high frequency expression of high frequency component along y-axis. So XLR means the low frequency component, and those 3 subbands means the high frequency component. So we can get the high frequency component as X, and after that we average these 3 subbands for high frequency image. So as a result, images with high frequency component tended to higher endpoint T-star values, but images with low frequency tended to have lower endpoint T-star values. So as you can see here, the high frequency, in the case of high frequency image, the endpoint T-star was 45, and for low frequency image, you can see that endpoint T-star was 25. So high frequency images require less time to be reconstructed than a low frequency image. Let's move on the method. So after discovering the relationship between a frequency component of image and the endpoint T-star, we proposed the wavelet-based optimization estimator, which predicts the endpoint T-star based on the frequency component of the image. And the models include those 4 components. X-origin means original image, and XLR corresponds to low frequency image, and X-sum means high frequency image, and ZT is DDI may contain time step T. And GT label is going to be T-star. And our training objective is learning to predict the remaining time step interval until the endpoint T-star. And the wave, and let's explain our model detail. And our model consists of wavelet encoder, image encoder, and attention module. So, and firstly, the wavelet encoder takes low frequency and high frequency images as input, and this image encoder takes the original image as input. And after that, these features are concatenated to obtain the visual feature. And after that, visual feature serves as the query input to the attention module, and DDIM latent ZT serves as key and value input, as you can see here. So our model performing cross attention, and afterward self attention is performed twice, and the final features undergo regression to predict the endpoint T star through an MLP. And we employ L2 loss and hinge loss for loss function, and yeah, these loss functions help the regression of our objective. So I briefly explain experiments and results. We use 50 images from other image editing tasks, and since the models include the DDIM latent ZT, so we can construct the number of T star samples for each image. And finally, we constructed 750 samples for training and 250 samples for validation and test. And we use AMSE for evaluation metric, which predict T star and is calculated between predict T star and ground truth T star. And after training of each epochs, the test MA converged to 2.9. So it means our model can predict the T star within a 3 time-step margin. So using wave of estimator enables image editing with an average of 28 seconds. So this result means that our model can reduce over 80% of the editing time compared to their text inversion, which takes 180 seconds. And it can be used in conjunction with optimized based method other than their text inversion. So there are the result of NTI and wave of estimator. As you can see here, our method shows similar or better editing performance compared to NTI. And especially since null text inversion optimized the null text embedding vector across entire time step, so it enforces excessive constraint on the original image, and it potentially limits the flexibility in the editing process. So our method, by optimizing up to specific endpoint, offer a more flexible editing. So among these result of NTI, the black hat does not change it to black, and it retains the characteristics of original image. But however, using our model, it is possible to more flexible edit. And additionally, this white cat also still have some characteristics of original image, like the stripes. So yeah, so thus our method achieve more flexible edit, and our model can reduce the editing process time. Thank you for listening.
Okay, we are open to any questions. Please feel free to throw any questions.
So I have a question.
Yes.
So your method based on the NTI, and then you somehow predict the time state, or that you just do a certain time state, not until the end, and you train a model to predict that optimal stopping time state. So my question is, where do you get the ground-truth time state for training the model? So you have optimal time state for stopping, and you train a model to predict that optimal time step.
Yes.
How do you get the route through time step for stopping?
We manually select the end time, the GT label for our 50 images. So that is our.
So you control the data set and you label the optimal time step for 50 images.
We manually select it and run through time step.
I see.
Any other questions?
Thank you for the presentation. I understand that it got a lot faster. And which part made it so that it has more flexible and better edit?
Because actually NTI method optimize the null test embedding vector across the entire time step during denoising process. So the NTI method enforces the excessive constraint on the original image to edit the image. But however, our method optimizes your text embedding vector only up to certain time step. So I think this part help the more flexible editing features.
Thank you.
Any more questions?
Can you tell us again about why you use the wavelet transform?
The purpose of wavelet transform. Actually, we want to separate the low and high frequency components from the original image, and there are two options. First one is free. Actually, we can use the free transform and wavelet transform, but in our experiments using free transform, we can perfectly separate the low and frequency image. But however, when we use wavelet transform, we can get a clearly separated image, low and high frequency. Yes. But theoretically, it is same.
Any more questions? If not, thank you for your great talk today.
Thank you for